Okay, good morning everybody, and welcome back to Dynamic Optimization. In our last session we concluded that it might be a sensible idea to not compute the value function for each possible point that we might think of, or each combination of different states and actions that we might think of, but to approximate the value function using a continuous function, which makes sense sometimes in even discrete settings if the state space is very large, but which is of course a necessity if we have a continuous state space. Then we can no longer compute the value function or the action value function at every point on the state grid. So what we are going to do in today's session is to give you an introduction to neural networks in order to approximate value functions as one application, of course, but also in order to approximate any possible function you might think of. What we have seen in the last time is a little bit new vocabulary, because now we are not representing the value function or the action value function by a very large array or a cube, like the cube we used last time, or even larger objects, even higher dimensional objects, but we are only representing the value function by the functional form of our approximation function and an additional set or vector of weights. This vector here does not necessarily need to be a vector inside R. It might also be a matrix or a list of matrices or any other kind of object in R to store this a bit more conveniently. But in here and for the applications we are looking at, we just call this one a vector, although it might be a matrix or might even be higher dimensional in R where we apply this later on. And then we denote by v hat and q hat the approximations, so of the value function and the action value function. And by nabla we denote the gradient operator. We'll see in a couple of minutes why and how we need the gradient in reinforcement learning. Then we've come over to the very first approximation method. That is just the linear approximation, where you just compute the weight vector transposed times our features that we create from the matrix and from the data, or from the states actually. And this is a very simple approximation because it is linear in the features, and then the gradient, of course, with respect to the weights is just the features. Then one might ask the questions, how can we construct features in order to represent the states properly? Because if we are only looking at the pure states, so the feature would just be the state, then the linear approximation doesn't really make sense in many applications, because then it would only be a linear function of the states. Of course, most likely the value function is not going to be linear in the states, so we need to come up with some idea how to construct features if we're using linear approximation. And then we have seen that there are at least 3 methods by which we can get the states, get interesting features from the states. So for example, we can use polynomial basis, and in this term we can also then add quadratic, cubic, or any kind of interaction term between the states or between just the states and the quadratic other states and so on. So we could also use grid approximation, so every state close to some point on the grid will be the same as this point of the grid, so that is aggregating some values of the state to be in the same value. And we have seen the tiling approach, which lays a set of grids over our state space, and then the features are either 1 or 0 for each tiling. So each tiling is either 1 or 0 if the point of the current state does not lie inside the current grid of the current tile. These are just some methods for overview, because we are not going to continue with linear approximation, but we are using now artificial neural networks as a nonlinear approximation scheme That, by the way, can also be a linear approximation, but we'll see that in a second. So what we are doing with artificial neural networks, basically, and oversimplified, is to replicate the mechanism of a nerve cell. And you can see a nerve cell down here. This is a microscope image of a mouse brain, and in the green thing here is one of the nerve cells that is fluorescent with some color that makes it shine bright. And as you can see here, you have many in this object here, you have many small roots going all to this larger node in the middle of the picture. And from this larger node, we have a big strain of nerve cell going out and processing the signal that has been computed inside this node. And neural networks, artificial neural networks, work rather similar. We have lots of neurons, and we stack those in potentially many layers. This is just an example or a picture of a potential neural network. And what we are doing is we have input layers. That's the one input layer, the one on the left. And that one is, in most cases, is our states, or sometimes it's sensible to normalize the states, so to get rid of the expectation and set the standard deviation to 1 in order to improve the learning quality. Why that is the case, we will see in a minute. Then we might have potentially several hidden layers in between the input layer and the output layer. These layers, as you can see on the right-hand side, on the larger, on the zoomed-in pictures, they receive everything from the input layer. So the input layer distribute their inputs to the hidden layers. Then they compute something that currently is a black box here, but we will uncover that black box in a minute. Then they output something and distribute the output to all the other neurons of the subsequent layer. So we are working with what's called dense layers. So everything between two layers is connected with each other. So the output of this first neuron is connected to all of the neurons of the third layer, and the output of the first neuron of the third layer is, of course, connected to all of the neurons of the fourth layer, and so on. Finally, we have in red here an output layer that is collecting everything from the penultimate layer, computes against something. Again, this is a black box for us now, and then outputs either a single value, or it even might output multiple values. It outputs a single value. We might also have more than a single output node in here if we are using a classifier and we want to classify an object into different kinds. For example, we have pictures of fruit and we want to find out which fruit is shown on the picture. Then we might have several output layers indicating, for example, the probability of the fruit being a banana or the fruit being a cherry. And then we might have several output layers here, output nodes or output neurons here as well. In our case, of course, the output node is going to output our approximate value function. So how do these neurons work? We have, as I said, several inputs, and then there is a computation step, and then there is an output. What's going to happen in the computation? There's actually two steps. The first step is the simplest step. It's just a linear regression, namely of the output of the previous layer. This is multiplied with our weights, and we add b, which is called the bias here, so it's just similar or identical to the intercept in in a linear regression. So this would then be xij, so let's just call this the value of neuron j in layer I. So for example, of the second neuron, so j is 2, of the second layer, then I would also be 2. This one is the product of the output of the previous layer of the first neuron times the corresponding weight in our current layer, plus the output of the second neuron of the previous layer times the corresponding weight in our current layer, plus and so on. We do this for all of the neurons of the previous layer, multiply them with weights. And finally, we add our constant term b. So basically just a linear regression inside the node. That is what's happening inside. And then we put the result of this regression to an activation function. And the output of our node is just the activation function of the linear regression. That's how a single neuron works. And if we stack many of those together, of course, we get many outputs in each layer, and we compute these all through the net.
I have a question here.
Yeah, totally.
So in the previous slide, we had many outputs in the layers in between, right?
Yeah.
So how does it work there? Because we had this yellow one, we have many outputs also, right?
No, if you have a close look at this graph here, we have a single output, and this output is distributed to all the layers.
Ah, okay.
So it's the same output, just distributed to all, not to all layers, to all the neurons of the subsequent layer.
Okay. Thank you.
Okay. Any other questions? Right, then the only thing that's left to talk about, or not the only thing, or one thing left to talk about is what might the activation function be. And there are, of course, the activation function in theory can be anything. It can be just a linear function, it can be a quadratic function, it can be a square root function, a log function, whatsoever. But some functions have turned out to be relatively useful in learning and in learning with neural networks. And the simplest function is, of course, the linear function. Well, fx is just x. Then we output the output of a linear regression in each node, and you can show that then the neural network is nothing else than just a simple linear regression model, written down in a very complicated way, and maybe with way too many weight terms, because you could also do this with far less weight terms if you just perform linear regression. But the prediction of this neural network would then be the very same as the predictions of a linear regression. So that's the most simple case. One very useful case that has been used widely in the past, but nowadays isn't used that often anymore because it has its downsides as well, is the sigmoid function. So 1 divided by 1 plus e to the minus x. And remember, x is again the output of the linear regression. So this turns each neuron into a logistic regression neuron in total. What's also interesting always is, because we'll see in the second half of today that we are learning using the gradient and using the derivatives, is that the derivative of a sigmoid can be computed very conveniently just as the sigmoid times 1 minus the sigmoid. That's the derivative of this function. If you apply the derivative rules on this here, then you will see that directly. One downside of the sigmoid function, and let me show you that right away, although you don't really, because when we're using the derivative to learn, is that for both cases that x is very small or x is very large, the derivative is basically 0. So for very large input values or for very small input values, we don't learn a thing, which is problematic, because if we specify the net a bit incorrectly at the beginning, or if we have a too large learning rate, then our gradient in the end will deteriorate and will turn up with zeros everywhere, and we will stop learn anything any further because the derivative then will be 0. We'll see that in a second. A third function that has gained much importance, especially since Google published a paper on image recognition using the Swish function, because it works much more, in their paper it worked pretty well, is then the Swish function is just x times the sigmoid of x. So we have a lower part going from minus infinity to roughly 0, where the function is close to 0. It has a small negative part down here, and then the function is basically just linear, which gives it a nice shape, and it's a smooth shape. So we have a derivative everywhere. We have no kinks in the derivative, which is a very good thing for us to have. And as you can see, the derivative at minus infinity or at large negative values is still 0. So it might happen that you end up with a gradient that is close to 0. But in the upper side, the derivative goes to 1. And in between, there's a smooth transition of the derivative. Then two more functions that are very simple and have worked rather well in the past in learning exercises is the rectified linear unit. It's linear above 0 and 0 elsewhere. So if x is larger than 0, then the ReLU function is 0 as well. If x is larger than 0, then the ReLU function is equal to x. Otherwise, it's 0. Making the derivative being either equal to 0 for anything smaller than 0 or 1 for anything larger than 1. So this one, of course, really profits from its very quick computation. You can compute the gradient easily because the derivative is either 1 or 0, and you can compute the function, of course, very quickly as well because, again, it's either 0 or x. There's not much computation compared, for example, to the Swish or to the Sigmoid function. And then last but not least, there's the Leaky ReLU function, working a bit better sometimes as the ReLU function because it has a slightly positive derivative for anything that is smaller than 0. So it is 0.001 times x if x is smaller than 0, and it's x, so like the ReLU function, if x is larger than 0. So then the derivative is either slightly positive or 1. So again, both derivative and the function itself are computed very, very quickly. Let's have a look at two examples. One example is a very small network where we want to make a forecast whether or not the sun is going to shine tomorrow or whether the weather is so cloudy that you won't see the sun at all. And we can do this by including, in this case, 7 states a month, the precipitation of the previous day, the air pressure, wind speed, wind angle, humidity, and temperature. And all these then will somehow give us a probability of whether or not the sun is going to shine tomorrow. In this case, we are going to forecast and we want to learn a probability. And in this case, of course, it makes sense to use a sigmoid function, for example, as output function of the final layer because the sigmoid, as you can again see here, only ranges between 0 and 1. So this one would be a very good choice if you want to forecast the probability in the final layer. In our examples, we have, if we, for example, might look at our car rental again, we might have as states the returns in location A. This is all of yesterday, so the returns yesterday in location A, the rentals in location A, the returns in location B, the rentals in B, and the prices in location A and B. They might, of course, all change over time. So this is not exactly taken from the exercise that we have seen before, but from a hypothetical car rental where you have, for example, returns and rentals not as IID or as white noise, but they are, for example, can be described in an AR1 process. Then these, of course, are all states that we might be interested in. And for example, the season might also indicate that in Christmas season that there is, of course, a spike in rentals, and in summer season there's also a spike in rentals, whereas in September or October we won't see many rentals, so we won't have a very large value function there. In this case, we do not want to approximate or do not want to forecast the probability, but we want to forecast our value function. So what is the value of our current cash flow plus all the discounted future cash flows? So potentially a rather large number. In this case, we are stuck here if we are going to use the sigmoid function, of course, as activating function in the output layer, because this one can only take values between 0 and 1. And in this case, we might go either with a linear function or with the Swish function and put either Swishs or linears in the intermediating, in the hidden layers as well. Remember, if we only put linear layers in here, then the result also is going to be linear. So maybe it might be a sensible idea to use some of the semi-linear functions, so the Swish functions in the hidden layers, for example, and the output function might well be a linear function. Because if we put a Swish function in the output function, then the value we are going to receive cannot be smaller than 0, which of course our value shouldn't be smaller than 0, but it might be that for some states and some action, the value might be very small, at least in the beginning of the learning process where we don't know anything yet about the value function. So bear in mind that the choice of the activation functions and the choice of the sizes of the network is of course up to you, but you should consider especially the choice of the activation functions, so that the activation function suits the application that you're going to run. In this case, of course, this small network with just 3 hidden layers would be way too insensitive to any of the states, to the number of the states. So there should be a much larger and broader hidden layer here, like at least 20 or 50 nodes in here to represent the value function based on the states and based on the different values that the state space might take. So to be able to be flexible enough here. So this small network here is just an example of how it might look. It's not a very realistic example because the hidden layer is way too small here. Okay. Are there any questions?
Yes. Yes, there's one. I've got one question. We have seen on the previous slides about tiling that there is something which you call the feature of the states. So it's a function x which depends on the states. Are the features apparent in these appearing in these neural networks as well? So is the input layer a layer of feature values, or is it the states themselves?
Sometimes it's both. It's not in such a systematic way as it was in the linear approximation, where we chose a method of creating features, and then you systematically used this method, for example, the polynomial base, and you said, okay, I want to see every combination of states and so on. But of course, the hidden layers can, by their large number of neurons in there, and if you stack many hidden layers in there, it gets even more flexible. Then these hidden layers can represent any combination or any nonlinear term of the states as well. So it's not as systematic as an approach to select features and then feed these features into the neural network. But in most times, the feature that you extract from the state is just very often the standardized, the normalized state. So you set the expectation to 0 by subtracting the mean of the states and dividing by the standard deviation of the states in order to have all of them in a similar magnitude. That often helps learning, but it's not really necessary to extract features in a systematic way from the states, because that's what the net is going to do implicitly. So you won't actually see the real features, but they will be computed internally in the hidden layers. Okay, then what we have is some hands-on artificial neural networks exercises. Some of them are pen and paper. Some of them work with code that I uploaded to the LearnWeb. I think it's called Neural Networks DynOp, that contains lots of functions to work with neural networks. We're not using a package here, but handwritten code, because that's at least a good way to both look how the functions work and to get results we can actually use for reinforcement learning, because we are working on a rather low level here, because we need the individual gradients later on, and we need certain things that you won't get from some of the packages. All right, then I'm going to start the breakout sessions, and we'll see us there. Okay, welcome back. Let's just briefly go through the solutions for the second part of the exercise, because the first one was pen and paper, and I think everyone should have gotten 0.9991 as a result of that. Let us just start with, the first step was to source this code, and to source code you just click on the source button in the top right next to the run button, and then everything from a whole code file will be run at once. So that's very convenient if you have large code files containing many functions and you want to have the code for all of them at the same time, or to load this, and you don't need to mark all the code and then go and run. A little mistake from myself, the net save function needs a required tidyverse before it works. So you either need to have loaded the tidyverse anyways, or you need to put in the line required tidyverse as the very first line for the net save function in order to store the net on your computer. That being said, let's have a brief look at the exercises. So the first thing was that we should create a vector of sizes for the two layers, and of course the first layer was of size 3, the second layer was of size 1, because we only had a single output. And the first layer's activation function is just input, which means the values are just distributed to the next layer. No computations take place. So nothing really happens there, but the net, of course, needs to know that nothing must happen there, and we don't need any computation. And the second layer is, of course, a sigmoid function. So let's just run these two lines so everything is in our environment. And with these two lines, we can then create our net with a net create function given some sizes and some activation functions. So let's create that net and let's have a look at this net. And the net is initialized in a way that the standard deviation of the output has a certain value, so I think it's close to 1, in order to achieve at least okay-ish working learning rates if you use sigmoid functions, because then the gradient will not deteriorate, at least not deteriorate that quick using these initialized weights. Obviously, these are not the weights that we have used in the previous example, so we need to reset them manually. And we can do this by saying that, let's have another look again. We need to set the second layer's weights, so these weights, and the second layer's bias, just a single bias because it is only a single neuron. We need to set those to the bias to -1 and the weights to 2, 0, and 1. And we can do this and at the same time maintain the structure, because these biases and weights are always stored in matrices by taking the current weights, multiplying them by 0, and then add the vector 2 or 1, and taking the current bias, multiplying it by 0, and adding or subtracting the 1 here. If we do this, so we adjusted our biases and weights, and then use the net IO for input-output function with our current net and with the with the data vector 3, 1, 2, the one that you should use in the first part of the exercises, then you could see that you get the same result as you had when you computed that yourself. So actually just the result you wanted to have. So if there was a different result, then something in this net is definitely broken, but now the result is the same, so that's good for us. Are there any questions regarding these exercises, or did you struggle at certain points and didn't find a solution? Okay, good. Then let's switch from just looking at neural networks and computing the output of neural networks, to how we can learn with these neural networks. What we wanted to do is to approximate the value function, and we are optimizing here. So we want to find a maximum of our value function because we're maximizing, want to maximize the rewards or the returns from our policy. And we can use this, we can do this by using the gradient descent method. So what we are doing there is we compute the derivative of the derivative of our value function approximation or our action value function approximation with respect to both the weights and the biases. And from now on, and always actually, the biases are subsumed in the weights vector W. So whenever you read the vector W, it also includes the biases. So we are not only updating the weights of the neural network, but also, of course, the biases. They are also in this, what we used as a vector object W. So any update rule you'll see later on will, of course, include the biases as well. And we can do this using gradient descent, or in this case, gradient ascent, because we're going to the maximum. The following way, we compute the gradient, and the gradient tells us, okay, if I increase weight 1, how much does the value function or the value function approximation change? And if the value function approximation increases in direction of that weight, then we would go into the direction of, then we would increase that weight, because that would increase the value function for us. If that weight decreases the value function, we would go in the opposite direction, so we would again increase the value function. But we have to specify how large our steps are going to be. We have used this learning rate parameter alpha before, and we are going to use the alpha parameter here as well. Because if you can see, as you can see in the middle picture, we have a very large value of alpha. Sorry. And the right-hand side picture, let's begin with the right-hand side picture. We have a very large value of alpha. So we make very large steps on the x-axis here because we only have a single weight and our value function is just a quadratic function here, so a very simple example. And we would find the optimal weight or the optimal x to maximize the function y here. If we take large steps, so we start, for example, at this -3. If we take large steps, this large step would bring us directly to something close to +4, a little larger than +4. So we made a very big step, increased our value a bit, that's true, but not by very much. Then we have a strongly negative derivative, so we do no longer go in direction of x, but in the opposite direction, so to the left, still increase our value function by a bit, but not that much, and are then again have a positive derivative. So we would go to the right again, to the left, and so on. So that happens if our alpha value is too large. On the other hand, on the left-hand side, if we have a very small alpha value, we have a positive derivative at -3, for example, here. Then we go a tiny step to the right, go, of course, up by quite a lot, but because we have a positive derivative here, but we make only very small steps to the right and to the right, so we find our maximum rather slowly. And in the middle, we have a value of alpha that is working very well. For this case, 0.3 seems to work very well because in the first step, we make a big step to the right, still are left of the maximum, or not right of the maximum. Then we make a little smaller step and another little smaller step, and after roughly 4 or 5 steps, we are at the maximum of this function without having overshot the maximum here. So finding alpha or finding a good learning rate alpha is important for this simple task here, and it's actually crucial for learning with neural networks, because if alpha is too large, then it often is the problem that our weights would either increase to infinity very quickly, especially if we have deep neural networks, the gradient increases drastically and very fast, and after a couple of iterations, all what our net would output us is just infinity. Or what could happen is that the gradient doesn't go to plus infinity, but it might also go very quickly, especially in deep neural networks, to 0, and then we won't learn anything anymore, although alpha is set very large. A very small alpha, on the other hand, makes learning very slow, but that is not such a big problem. So if you start at a value that is too small, you can just gradually increase over not over iterations inside the algorithms, but over running the algorithm a certain kind of certain times yourselves. And by running the algorithm multiple times, you learn, of course, what a good value of alpha is. There is not really a rule of thumb for that. It always depends on the application that you have. And so this is just trial and error to find suitable values for alpha. Now, that being said, that we want to use gradient descent, we only need to compute the gradient. And to do this, first let's briefly talk about how to use gradient descent in reinforcement learning. I already said that the gradient tells us how much the function increases or decreases if we increase by an infinitesimal amount, increase our weights by a small amount. So just the derivative. Let's now assume that, and we've seen this before, that the reward plus the discounted future action value is larger than our current action value. That means then that our current action value underestimates our value function probably. So we would like to increase that. So we would, in this case, go into the direction of the gradient. Whereas if the current reward plus our discounted future action value is smaller than what we currently know about the value function or the action value function, then we would, of course, like to decrease the output of the value function, and then we would go in the opposite direction. So in the opposite direction of the gradient. So the gradient determines a step size or a step length and a direction, but also the difference of the value function and the reward gives us a direction in which to go, because these two together determine whether or not we want an increased or a decreased value function. Now, how to compute the gradient? It's in a neural network, it's a bit more complicated, but actually it is just a way of cleverly using the chain rule. It's called the backpropagation algorithm, and I think we can use the final, what's left of today, so 7 minutes, to just briefly go through this algorithm and through the idea of the algorithm, because basically it's just applying the chain rule multiple times for each layer. First of all, we denote the output of all the nodes of layer j by zj. So what we have denoted by f of x or by f of x, or what we've called O in the previous slides, now is the variable z. Then obviously q, so the approximation itself, is z at the final layer j. If we are in any of the layers, we can define then our x, and we might really call that the feature. So it's because it's just linear of our previous output. So we might call that just for now features. Is defined as the biases plus the weights times the output of the previous layer. So what we have actually seen before, so the same definition we have seen before, but in the final layer, we see that the output of this layer, that the feature then of this layer is just z. Because there's no further computation. Once we have computed the activation function of the final layer, then this will just be outputted. And then we can, with delta, describe the derivative of our value function with respect to the feature. And what would then be missing is the derivative of the feature with respect to the weight, and then we would have the complete derivative of the action value function with respect to the weight. So having this ingredient, we are only missing one ingredient that we'll look at in a minute. So the derivative of the action value function with respect to the axis of any of the layers, of layer j, is then the derivative of the action value function with respect to x at the jth, capital Jth layer, times the derivative of x at the capital Jth layer with respect to the x at the previous layer, and so on and so on. So we're going from the last layer, from the final layer, through the net, and use the chain rule with these derivatives. But if that's the case, we can just write down that delta j is delta j plus 1, so the delta j of one layer further in the back, times the derivative of the input for our activation function at layer j plus 1 with respect to the input for our activation function of layer j. So if we know delta capital J, or delta capital J plus 1, we can then go, the delta capital J, we can then go and iteratively compute the derivative beginning from the output layer, going back to the input layer. And that's why the algorithm is called back propagation, because we are putting the derivative into the net and going back into through all the layers. So what we are left with now is to compute this derivative here. But that is pretty straightforward, because this derivative, the derivative of xj plus 1 with respect to xj, we just plug in the definition of xj plus 1, meaning xj plus 1 is b, j plus 1 is missing here, plus the weights of the j plus 1's layer times the output of the previous layer, and then the derivative of that with respect to x. The b's, the weights, of course, don't have a derivative with respect to the x of the previous layer, so the output of the previous layer of 0, because the weights don't depend on this term here. But what we have is that we have the derivative of z, so of the output function, of the derivative of the output of the layer with respect to the input of the layer, or at least of the input of the activation function. So this term here is then the Jacobian matrix of the activation functions with respect to their inputs. Basically, this term here is a matrix that contains all the derivatives I showed you here on these slides. So for example, if we have a sigmoid activation layer, then this Jacobian would consist of sigmoid times 1 minus sigmoid and then evaluated at the point x. So that one is also very simple to compute, because we already know all the activation functions. We know the individual derivative of all the activation functions, because the individual derivatives are very simple to compute. And we only need to multiply this with the weights, because that term is in here. It's just the product of weights and z. Now to finalize this, what we wanted to see was not the derivative of q with respect to x, but what we want to see is the derivative of q with respect to w, or weights. So how do we need to adjust our weights to increase the value function? And that's nothing else than the derivative of q with respect to x times the derivative of x with respect to w. Just apply the chain rule again, because x is just defined as b plus w times z. This term here on the left, we know that was delta j. We just defined that as delta j. This one here, the derivative of xj with respect to wj is nothing else than the output of the previous layer. Also, that follows from this definition. So derivative of this with respect to the w's is just the output of the previous layer. That would be then the gradient with respect to the weights, and the gradient with respect to the biases is just delta j, because the axis, so the regression part of the neural network, has a derivative with respect to the biases, of course, of 1, because it's just a constant. If I increase the constant by 1, then the x would also increase by 1. So pretty simple, this is just 1. And we have delta j in here as gradient for this weight. Luckily, everything of this has already been coded, so you don't need to code the gradient yourselves, which would definitely is out of the scope for this course. So you can just use the gradient operator or the gradient functions in the code I just gave you. And we will do this. We will start with an exercise regarding the gradient in the next Tuesday session. So are there any open questions for today? All right, then I wish you a nice day and see you on Tuesday.